Okay, good afternoon, everyone. My name is Jean-Camille Chassin. I'm a professor in fluid mechanics at Sorbonne University. And it's my pleasure to chair this PhD defense for Madame Cécile Roques. And let me start by introducing the members of the committee. Gaël Poète, researcher at CEA. Paola Cinella, professor at Sorbonne University. Grégory Dargam, research engineer at Safran Tech. Xavier Merle, associate professor at ENSAM. And via video conference, I guess, we have Francesco Montomoli, professor at Imperial College. Hello, Francesco. Do you hear us?
Non, mais pas ton son. Est-ce que ça doit être... Normalement, ça fait un haut-parleur, ça aussi.
Francesco? Also, Didier Lucor, research director at Lycen. Hello, Didier.
Oui, c'est moi qui suis connecté à ça.
Zoom pas loin.
Alors attends, il faut que je la récupère. C'est ça. Ah, oups. Plus. Et après, je fais quoi?
Ça va dans audio et plutôt la petite flèche.
Déjà, est-ce qu'on peut regarder dans le
meeting de
chat.
Oh non, c'est bon, t'es dessus.
Ouais, normalement, c'est connecté.
Non, pas du tout.
Ok.
Ben, je peux peut-être mettre juste l'audio de mon ordi et... Can you hear me now?
Hello, Francesco. Didier.
Can you hear me?
Ça marche maintenant. Moi, j'entends bien.
Okay. So I'm just going to speak on my computer because the microphone from the room doesn't seem to work.
Ok. Hein? Yeah, oui, Francesco, il entend.
Non, mais ça sera pas connecté.
Okay. So, Cécile, I think we are now ready to hear your presentation of your research work.
Thank you, Jean-Camille, for the introduction. Thank you for everybody that came here or online to learn more about the work I did during my PhD. So, for the last 3 years, I have been working on turbomachinery flows and more precisely on how to improve the numerical simulation of such flows. They are typically found in aircraft engines, such as the LEAP-1B engine that equips most of the single-aisle aircrafts. And such engines are composed of a few key parts. So first, the fan that pulls the air into the engine, that then goes into the compressor where its pressure is raised, and then passes through a combustion chamber in which the air mixes with fuel and ignites. And then the high temperature, high pressure flows passes through turbines that supply the power to drive the fan and the compressor, and then they are accelerated through a propulsive nozzle that is not depicted here, but that provide the thrust to move the aircraft. So those engines require intensive and interdisciplinary expertise to develop and design. And we are just going to focus in my work on the fluid dynamic problems, and more precisely, the computational fluid dynamic problems. And because on the fluid dynamic problem inside the rotating equipment, so more precisely on the compressor. And because a real compressor is a really complicated configuration, in my studies I only focused on simplified configuration, and I studied two configurations. One two-dimensional infinite and linear cascade of compressor blade and one three-dimensional. So a few simulation strategies exist, ranging from direct numerical simulations that simulate all the scales of turbulence. They are high fidelity but high cost, and for such flows, high Reynolds flows, such as in the configuration studies, they are not computationally tractable. And so that is why in the industry, most simulations are conducted through Reynolds-Averaged Navier-Stokes models that models all the scales of turbulence, so are less costly, but also less accurate. And more precisely, in my work, I studied 6 Reynolds-Averaged Navier-Stokes models that are widely used in the literature. So, and all the simulation were conducted by using the ELSA solver from the ONERA. Because the RONS simulation strategies involve using models that model all the scales in turbulence, they introduce in themselves a few sources of uncertainty that we need to make an inventory of. So we can classify them in 3 main categories. So the first source of uncertainty would arise from the averaging operation, that is one of the fundamental equations of such models, that introduces in itself the need for a model. Then, when we need a model, we need to find a modeling strategy. So what type of model do we want to develop? Are they going to be linear, more complicated? And what is basically the mathematical form of the model? And there's many models that exist, and there's no clear consensus on which perform the best. So there's introduced uncertainty in here. And finally, the last source of uncertainty in a RANS model comes from the value of the parameters used to close the model. And because the first source of uncertainty is fundamentally irrecoverable, it arises from the need of a model itself. It is not reducible. So we are only going to focus in my work on the last 2 sources of uncertainty. And as I said before, the RANS modeling strategy is the main strategy used in the industry and is widely used to simulate turbulent flow. So a lot of research has already been conducted on trying to quantify and reduce such types of uncertainty. And so I will not have the time to develop all the strategy that exists, because there are many of them, but for the models form uncertainty, we can classify the research into 2 main categories. So first, the intrusive methods. So basically, in intrusive methods, researchers try to introduce a corrective term that is learned from data within the constitutive equations of the model. So we need to develop, to do that, we need to develop and add a correction term within the equation, so within the computational fluid dynamics solver. And these developments are not straightforward using an industrial solver. And so that's why non-intrusive methods try, on the contrary, to quantify and reduce the uncertainty associated to the model form by leveraging the large variety of models that exists and try to create ensemble methods to quantify those uncertainty. And for example, my work follows on the work by Maximilien de Zordo-Banlia, which developed methods to aggregate models using space-dependent weights, so leveraging the best model at the best place. Similarly, to quantify the parametric uncertainty, so the uncertainty associated with the value of the parameters, 2 main strategies can be followed. Either the direct propagation of a known uncertainty through the solver to try to understand how it impacts the output of the solver, or the resolution of an inverse problem, so using Bayesian calibration to update knowledge based on data. So in my PhD, I try to develop frameworks to try and quantify those two types of uncertainty at the same time by using the aggregation of models and Bayesian calibration. So basically, the goal of Bayesian calibration is to provide a distribution, a posterior probability distribution of a quantity by updating our prior knowledge using data. So it is based on the Bayes theorem, and we try to learn the posterior distribution of the model parameter. And here, the model inadequacy hyperparameter that have been introduced to try to quantify the structural inadequacy of the model to capture the data. So to get the posterior distribution, it is directly proportional to the prior distribution of the parameters and the hyperparameters, which indicate the prior knowledge we have on such parameter and hyperparameters, and is also proportional to the likelihood, that is the probability that the model will match the observed data using those parameters. And so the likelihood requires the call of the computational fluid dynamics solver. So it is not possible to have the analytic to solve analytically the likelihoods, and so to get the posterior distribution. That's why it requires sampling from the posterior distribution. And in my work, we used the net sampler in PMC4. And so once we have the posterior distribution of the parameter and hyperparameters, it is possible to compute the posterior predictive distribution of the quantity of interest, so delta Arens, by basically propagating the posterior distribution through the Reynolds models and computing this integral. So before diving into the complex and the complexity of Bayesian calibration of Reynolds models, let's try to understand how it works on a simpler data set. So we can see, like, for example, a measurement of pressure as a function of x. And we can ask ourselves, what is the best model to predict this data? So many models can be envisioned to try to simulate and reproduce this data, either linear model, cubic model, or even more complex one like sinusoidal or logarithmic one. And a priori, we can't say which model is the best to reproduce this data. So if we use the Bayesian calibration framework I presented you just before, it is possible to compute the posterior predictive distribution of the model prediction for each more simple model. And from this posterior predictive distribution, we can compute the mean, depicted in red in each of the figures, and the 95 confidence interval, so a measurement of uncertainty. And we can see that for each model, the observed data is almost included in the 95 confidence interval, but the width of this interval vary greatly between one model to the other. And we can see that the width of this interval is directly linked to the value, the a posteriori value of the hyperparameter sigma eta. And the bigger the hyperparameter is, and the wider the 95 confidence interval is going to be, and so the less accurate the model is going to be. So let's get back to computational fluid dynamics applications. And let's say we want to predict the total pressure field on a two-dimensional infinite compressor cascade. And we want to know which model is the best to predict this data between four widely used Reynolds models. So the Wilcox K-omega model, the Lander-Sharma K-epsilon, the Spallard-Talmaras model, and the Smith-KL. We're gonna try to quantify, try to find out which model is the most accurate based on the training scenario with an angle of attack of 49%. And because no high fidelity data was available to calibrate our RANS model on, we're creating a synthetic data set using another but more complicated RANS model to try to understand how the Bayesian calibration framework works on on a more complex configuration. So, as I said earlier, the computation of the likelihood requires the call to the computational fluid dynamics solver, and sampling from the posterior distribution requires a lot of calls to the computational fluid dynamics solver, and it is not tractable to use at each sample the solver, so we need the creation of a surrogate model to make it computationally tractable. So many surrogate modeling strategies exist, and to do that we used proper orthogonal decomposition and kriging to model our RANS model. And so proper orthogonal decomposition suppose that the output of the solver can be decomposed into orthogonal modes that are composed of deterministic spatial components and random coefficient that depends on the parameters. And what's interesting that only a few modes are enough to capture at least 99% of the total variance. So we only need to use kriging for the first few modes that capture 99% of the variance, and learn the relationship between those coefficients and the parameters. So if we apply this to the model K epsilon, we can see that we only need 5 modes to capture 99% of the variance. And by then reconstructing using the proper orthogonal decomposition the surrogate model and plotting the mean absolute percentage error, we can see that there's a small error everywhere in the field because it is always less than 1%. So using this surrogate model, we can then sample from the posterior distribution of the RANS parameters and hyperparameters. And we can plot on these figures the posterior distribution in red and the prior distribution in green. So because we didn't have any knowledge on what would be the best parameters, we took uniform distributions. So first we can see that the posterior distribution are very peaked and they are not centered around the baseline values of the model parameters that are depicted in the green dashed line. We can also see that for most parameters, the posterior distribution is pushed to the bounds of the prior distribution. So this indicates that maybe we should have opened up more the prior distribution, but the bounds for the prior was chosen under numerical and physical considerations, so we cannot do it anymore. Also, the value of the hyperparameter sigma eta is quite low, indicating that we need to modify the model, but not as much, but not so much. So using the posterior distribution, we can then propagate them through the model to compute the posterior predictive distribution. And from this posterior predictive distribution, it is possible to compute the mean and the standard deviation that are depicted here. So it is interesting to note that the standard deviation is always very low. It is always less than 2% of the mean of the prediction. So this gives an indication on uncertainty relative to the parameters and their propagation through the code. And using the mean of the distribution, it is possible to compute the relative error with regards to the reference data, either for the baseline model or the updated model. So we can see that the mean square error, thanks to the calibration, is almost divided by 2. So we can see an increase in performance there. But it is interesting to note on the plot that the reduction of error is not spatially homogeneous because there's a great increase in performance near the trailing edge. So the relative error is decreased, but at the expense of what happens in the wake. So, for example, we can see that there's an increase in the relative error at the bottom side of the wake. So we can see on these figures that the K-epsilon model tends to specialize, to reduce the error in one certain area of the flow at the expense of the prediction elsewhere, with a great global reduction of mean square error. So we can do the Bayesian calibration framework for all of the models, and what we found is that we had improved predictive performances for all models. But when we try to use the updated parameters or the updated models on a different configuration, so on a different scenario with a different angle of attack, we've seen that many models, and more precisely the one that tends to over-specialize, like the K-epsilon model, have bad generalizability properties. And so the fact that some models, like the K-epsilon, are able to specialize in one area of the flow at the expense of what happens everywhere else, gave us the idea to take profit of this capacity to specialize, but to do it on purpose by creating local expert models. So basically, the creation of expert models, if we come back to our little toy models, it would say that what is the best data to predict, what is the best model to predict this data? It is it generally, or maybe on different region of our data sets, some models are going to be better than others. So it is possible to try to identify the different dynamics in the data set and try to recalibrate all the models on each specific dynamic. So when we did that, we can see that the model really now captures every specific regions with an inadequacy parameters that is now really low compared to earlier before, and that the mean and 95 confidence interval really captures the observed data. But we can imagine that now the prediction outside of the calibration region is going to be catastrophic. And what we are interested in predicting the whole data set and not only one specific regions. So that gave it the idea to add another step afterwards, after calibration, which would be the local aggregation of models. So basically taking the best model at the best performance regions. So to do that on the computational fluid dynamic problems, let's now consider a three-dimensional linear infinite compressor cascade. So in such flows, we can find a few different and specific physical dynamics. For example, the turbulent boundary layer on the hub or on the wing, a wake flow behind the blades, a corner separation between the hub and the blade, and the boundary layer separation near the trailing edge. So the first step we need to do to try and develop a local calibration and aggregation framework is how can we identify the physical dynamics that we're going to use for local calibration. So the first thing we tried to do was the automatic detection of such physical dynamic. I will not discuss it here in this presentation because I don't have the time. But it required the use of unsupervised learning techniques. And for that, we developed local flow features. And then the local calibration was was done using data from the configuration. So we used the data from the configuration of study. And the other strategy we studied in this PhD was to identify the physical dynamics using expert knowledge, because we as physicists can knows what physical dynamics are in the flow, and try to use smaller, simpler building block configuration for the calibration of the model. So we're gonna see in more detail these strategies. So the first step, as I said, was to identify the physical dynamic present in this flow and try to find simpler and smaller building blocks to represent them. So for example, for the turbulent boundary layer, it is possible to model it as a flow over a flat plate. For the wake flow behind the blade, it is possible to model it as a wake flow behind the flat plate. For the boundary layer configuration, it is we can use a flow over a backward-facing step to try to capture the recirculation region. And for the corner separation, we can use a flow in a square duct to try to represent this physical dynamic. So we are interested in this 4 building block configuration, and we want to calibrate, use Bayesian calibration to calibrate the models. So we were interested in this 4 specific building block configuration because experimental data sets and measurement of longitudinal velocity profiles, for example, are available. And we used those 4 experimental data sets to calibrate the 4 RANS models. So we used the Spallard-Talmaras, the Smith-Kael, and the same model with the QCR correction. So the QCR correction is a correction in which we add quadratic terms within the Reynolds stress tensor to try to better capture the turbulence anisotropy, which is exists and is important in flows such as flows with secondary flows, such as in the flow in the square duct, or where the streamline exhibits strong curvatures, like in the flow over a backwards facing step. And so calibrating those 4 models on those 4 experimental data sets leads for 13 updated models, because we are not going to, we only calibrated the QCR corrected models on the square duct building blocks. So we only have 14 expert models. So we use the Bayesian calibration framework to calibrate the 4 models on the 4 building blocks. And it is interesting to have a look at the mean square error of the baseline models and the updated models in each building block. And we can see that for most, for each building block and for each models, the Bayesian calibration step really improve the performances and really reduce the mean square error compared to the baseline models. Interestingly, in the boundary layer building block, we don't see a really impressive reduction of mean square error, but this is because this building block is used in the design of the RANS model. So we expected that the building block, the models calibrated on such building block will not improve as much the predictive performances. So now that we have 14 updated models, it is interesting to try to make cross-prediction. So using one model to predict the other, one model calibrated on one building block to predict the other building blocks. And so if we have a look at the mean square error for 2 of the building blocks, we can see that the better performing models are the ones that have been calibrating on the building blocks of interest. And so it really reassured us that we created expert models on one specific physical dynamic. And so now it is interesting to use those 14 building blocks calibrated on, those models calibrated on building blocks, on a more complex configuration. So the three-dimensional NACA65 linear compressor cascade. We're going to consider two scenarios on this configuration, one training scenario and at an incidence angle of 4 degrees and one testing scenario later on. And the big difference between those two scenarios is that there's the bigger corner separation for the 7-degree scenario. To compare ourselves, we used the time average velocity field from one large eddy simulation that was conducted by Dimitrios Papadogiannis. And so we used the 14 updated models I've just told you about. So using those 14 models, we can get 14 prediction using the ELSA computational fluid dynamics solver. Okay, so it is not really straightforward to visualize 3D fields. So we're going to have looks at span-wise slices. So here we are looking at the absolute error compared to the LES data for the QCR corrected KL model, either baseline or the one on the left calibrated on the wake flow building block, and on the right calibrated on the square duct building block at 10% of the span, so near the hub. So it is interesting to note that for the square duct updated model, the reduction in absolute error is important in what appears to be the corner flow, so on the calibration region. And there is no significant improvement or decrease in performance for the model calibrated on the wake flow. And if we have a look a little bit farther from the hub, so at a span of 50% of the span, for the same model, so the baseline, the wake flow updated, and the square duct updated, we can see now an important increase in performance for the model updated on the wake flow by the reduction of error within what appears to be the wake. And for the square duct updated models, we can see an increase in error in almost everywhere. So these results those results are really interesting because it suggests that our hypothesis that said that calibrating models onto small and simpler building block configuration would increase the performances within the same physical dynamics, even in a way more complex configuration and flow. And so also we can compute the mean square error for each models and compare it to the baseline mean square error. And we can see that generally, globally, the models are less accurate than the baseline models. But as we saw before, they are more accurate in some specific region of the flow. So we recreated expert model for one physical dynamic. And so this performance really motivated us to have a look on the aggregation of models, so trying to take the best performing model at its best performing in its best performing physical dynamic. And so for that, we developed space-dependent weights. And so they are defined as followed. The weights for model M, calibrated on the building block B, at one observation location xi in the flow, is defined as the model plausibility, given this data and the observation location. And the model plausibility is the probability that this model, given the set of model, is going to be the best performing model to reproduce this data. And this model plausibility is further defined as the pointwise marginal likelihood times the prior plausibility. So the prior plausibility is our prior knowledge of which model performed the best. And so because we don't have any a priori knowledge on which one would be best, they are a priori equiplausible and divided by a normalization constant. And so in this definition, the models are defined in the 3D space, though one observation location xi, but this 3D space, and so the weights associated in this 3D space are going to be geometry dependent. And so they're not going to be, we're not going to be able to use them on a different configuration, and that's not what we want, because we want them to be independent of the geometry. So that's why we want to interpolate them into a 10-dimensional local flow feature space, which is now geometry independent. And so to interpolate them in this 10D local flow feature space, we use the random forest regressor. So to train it, we used the features computed on the training scenario with a 4-degree incidence angle, and to regress the weights computed on the same configuration. And so for further prediction, we only have to compute the input features and use the random forest to get the predicted weights. So if we do this by training on the 4-degree scenario and predict on the same training scenario, to have a look of the space-dependent weights. So for the QCR corrected and updated on the squared KL model, we can see that the weight attributed to this model is almost 0 everywhere, except in what appears to be the corner flow region, in which this model is given a greater weight. So it is more trusted in its prediction physical dynamic, and not everywhere else. And also, if we now have a look at the same Reynolds models, but calibrated on the wake flow building block, we can see that globally the model is way more favored than the one before, except in the corner flow region, in which the model is given a 0 weight, and it's even more favored in the wake flow far from the hub, in which the model is given even a greater weight. So these results are interesting because we can see that models calibrated on simpler building blocks, such as the wake flow model or the boundary layer building block, are generally more favored than the model calibrated on the more complex building blocks, such as the separated boundary layer or the corner flow building block. So this variability in weights are interesting, as we now want to aggregate the models to take the better performing model at the best place. And so basically the aggregation of models, so the distribution, the aggregated distribution, the aggregated prediction, is basically the weighted average of each of the updated models' prediction, weighted by their respective weights. And so from this aggregated prediction, we can compute the mean of this distribution and the variance. And here the variance is mostly an indicator of how well the models agree with themselves. And so by using those equations, we can compute the mean and the standard deviation at different spanwise positions. And what is interesting is that within the potential flow regions, all the models agree together. So for example, if we have a look at the standard deviation at midspan, so in the potential flow regions, all the models agree together because the standard deviation is 0, which is reassuring because the turbulence models have no impact on there. And the standard deviation is way more important in the complex physical dynamics, such as the corner flow and, for example, the wake at midspan. And using those distributions, it is possible for us to have a look, to take another slice at different streamwise position now. So, and try to plot the mean of the distribution and the 95 confidence interval at different span-wise position and streamwise position. So it is interesting to note that most of the large eddy simulation data is included in the 95 confidence interval, but not all. And so maybe it suggests that there is still structural inadequacies within the Reynolds model, even with the QCR correction, that may not be sufficient to capture the whole large eddy simulation data. And so using finally the all aggregated prediction, we can compute the mean square error of the building block model aggregation, and we can see that it is globally way more accurate than any of the baseline models or any of the updated models. So that's really interesting because by this we developed a framework to try to reduce the error and give confidence interval with it. So now we want to try and test if this framework is generalizable to another configuration. So to a different testing scenario, which is have a bigger incidence angle. And so using the 14 Reynolds models, we can get the prediction. By getting the prediction, we can compute the features that can be then used to predict the weights. And it is interesting that when we look at the same model, the QCR corrected model updated on the square ducts, the weights are similar on the different configuration. So they are almost zero almost everywhere, except in what appears to be the corner flow regions. With so these are the predicted weights using the random forest. And because we have the data set, the large eddy simulation data set, it is possible for us to compute the true weights using the high fidelity data and compare them to the predicted weight using the interpolator. And we can see that they are quite different. Generally, they look a bit the same. So the models are not favored everywhere except in the corner flow, but the weights and the intensity of the weights are very different, and especially in the corner flow. And this might be, we can fear that this might reduce this prediction of weights step, might reduce the predictive properties of the methods in the prediction configuration. So if we have a look at the relative error of the aggregated prediction compared to the large eddy simulation data, so we can see there's a strong error within the corner flow and near the trailing edge in using the predicted weights, so the predicted aggregation of models. And when we use the true weights, we have a way less error at the same place than before. So this is what we feared, that the prediction step, the prediction of weight step, reduce the predictive performances of the prediction. But when we have a look at the mean square error of the building block model aggregation using the predicted weights, it is still most accurate than any of the baseline models. But when we have a look at the mean square error of the building block model aggregation using the true weights, we can see that it is way more accurate than the one with the predicted weights, and it's way more accurate than any of the baseline or updated models. So to sum up this methods, this methodology contains 3 steps. So first, the calibration on the building blocks, the computation of the space-dependent weights, and then the reconstruction of the aggregated prediction. So in the calibration step, we found that the posterior varies significantly from one building block to another. So this suggests that there's no universal set of parameters that can adequately capture the one physical dynamic. By computing the space-dependent weights, we saw that the models calibrated on simpler configuration were more generally favored compared to more complex ones. And this was expected because the simpler configurations, such as the wake flow configuration or the boundary layer configuration, are usually used to design and calibrate the RANS models. And finally, the reconstruction of the aggregated prediction showed a great improvement in the predictive performances, but there is still some generalizability issues in the weight prediction step using the random forest regressor. So to sum up this whole presentation, the goal of my PhD was to develop frameworks to try and quantify and reduce the uncertainties associated to the model form of the model or the parameter of the models using Bayesian calibration and model aggregation. So first, by recognizing that the global calibration of models produced undesired and uncontrolled specialization of models, we were able to create and try to work on two local calibration and aggregation methods, one based on clustering, so called clustered model aggregation, and the other one on building block model aggregation. So they are similar in their philosophy, but not in their implementation. And so both of them showed great significant improvement in the predictive accuracy. And while the clustered model aggregation showed straightforward generalizability property compared to the building block model aggregation, which have the interpolation of weights that seems to require a bit of work, the detection and calibration step of the clustered model aggregation framework was not straightforward, while the detection using expert knowledge in the building block model aggregation was more easy and more easy to implement. So based on those two conclusions, there's an interesting avenue of research that can be pursued. So the development of new calibration and aggregation methods that can leverage the generalizability properties of the clustered model aggregation and the building block model aggregation calibration strategies on smaller building blocks. And this would require the improvement of the automatic detection of the region step developed but not presented here, which here based on simple physics-based clustering of the flow that is also interesting to develop in itself because it is a very interesting research area. And so in conclusion, while the building block model aggregation and the clustered model aggregation frameworks still requires certain challenges to overcome, they offer a promising foundation for the prediction of turbulent flow with their associated uncertainties. Thank you very much.